So our discussion from Monday gave us what happens when we only have one item we are examining, one factor that we believe influences our response variable. So what happens when there's more than one? Well, I'm just going to go with the simplest version. I'm going to go with a two-factor idea. So let's consider I'll call my two factors A and B. And again, A and B are grouped. They're qualitative. They're temperature ranges. One of the examples at the beginning of section 11.2 dealt with the drying time for particular paint in different temperature ranges, and low temperature, medium temperature, high temperature. But I could also have three different kinds of paint, and I could ask which combination works best. And perhaps it differs in each idea. So I'm going to set up a grid this time. I'm going to have the different options for A in rows, and I'm going to have the different options for B in columns. I'm already looking like I'm going to set up a spreadsheet. But that's just explaining the fact that it says up there two-factor. It also says without replication. And that means that for each combination of factors, I only have one data value. So right here, I have a y value that goes with factor A1 and factor B1. That's our combination. That's called a treatment. And so here, there's one number for each possible row and column combination. Some texts call this non-repeated rather than without replication, but it's a non-repeated measures. Only get one shot at each combination. And remember, a combination of factors is called a treatment. Now, my hope, idea, goal, is that I want to see if there's some quantitative difference in my response variable y, depending on which row and which column I'm in. I'm going to play the same straight line game we played with one factor. And I'm going to say to myself, really, I'm going to think that each of these items has an effect from one grand central mean, because that's still our null hypothesis, that there's really no difference, no matter which A I use, no matter which B I use, there's really no difference. But there might be some effect due to my rows. There might be some effect due to my columns. And there might be some random error. And so for each possible J and K, this number is going to be somehow a combination of those things. But if I think there's some grand mean, I'm really testing two different things. I'm testing do the rows have an effect, and I'm testing do the columns have an effect. And then I'm looking at interactions. So I really have two sets of null hypotheses. I really have a null hypothesis and an alternate hypothesis strictly based on the rows. That all the row effects are equal. If that's my null hypothesis, what's my alternate hypothesis? There is another set of null hypotheses, exactly the same way set up for B's. So these are the hypotheses based around factor A. And these are the hypotheses based around factor B. If both null hypotheses are true, then there's one grand mean, and that's really all I need. Whew. But really, there's more than one test going on. I'm testing my factors A, I'm testing my factors B. I should not just get one F value. I should get two. I should be able to get a test that tells me whether or not the row matters. I should get a result that tells me whether or not the column matters. And they're separate to each other. So it is possible in some combinations of factors. We were talking about the example I gave earlier was paint drying at different temperatures. It could be that which paint you are using doesn't matter, only the temperature matters. We might have one set where the null hypothesis is true or accepted, and in the other one, it's rejected. It's possible to have both accepted, both rejected, or either one accepted or rejected. Questions? Again, doing the calculations themselves is tedious and nauseating. Just like with the calculations I was looking at for the single factor ANOVA, I have to take all sorts of squares and differences from my means and end up, no, not going to do it. Page 430, I'm not going to bother. We'll simply run the numbers in Excel or some other statistical software at this point and say, all right, what does this tell me? If I get two results, that means I get two F values. It also means, depending on the number of rows and the number of columns, which don't have to be equal, I could have two different F critical values because I'll have two different sets of degrees of freedom. So I need two different p-values. An example, page 433, number 21. Concerned about Friday absenteeism, management examines absenteeism rates for the last three Fridays in 4 different plants. Does this sample provide sufficient evidence to conclude that there is a significant difference in treatment means? Each combination of factors is a treatment. So I'm trying to say, hey, does which weekend it was matter? Does which plant it was matter? Maybe people from plant 1 are skiving off to go drinking. Maybe people from plant 2 are going to a football game. They're next to the high school. Who knows? Friday night, we'll go see the high school football game. Okay. What are our null hypotheses for this setup? I need hypotheses before I do any testing, before I do anything else. I need to know what I'm assuming, what I want to test for rejection.
It's not about bigger or smaller. So if it's just about the difference. If there's a difference, so I would use the two-tailed test.
Right. But I still need a hypothesis for this. So the hypothesis needs to be something about the rows and something about the columns. I need 2 null hypotheses, one here and one here. How do I phrase the hypothesis, Felix?
That one is equal to that 3 and 4. That's our one hypothesis. The other is that margin 4 is equal to that.
So the first hypothesis is that there's no difference in absenteeism based on which plant. The second is that there's no difference in absenteeism depending on which Friday. So the plant doesn't matter. They're all equal. The date doesn't matter. They're all equal. The alternate hypothesis in both cases, at least one is different. So now I would say, let's run the numbers. Here's the data. Exactly the same way we just saw it in the text, written up for Excel. That highlighted block up there, there are our dates down the columns. Sorry, across each row is a date, down each column is a plant. I'm going to do an ANOVA, 2-factor, no repetition. Again, when I go to tell this, I say, all right, I want to do some data analysis. Go to the data analysis tab. And way up here at the top, there are my ANOVAs. And lo and behold, the third one says without replication. So that's the one I'm going to do. Click. Okay. Now, where's the data? The data is in these blocks. Highlight the whole table. And I did include the labels. So I'm going to click that. And it by default does this at 5%, just like our others. If it tells me a different significance, I'm going to use that. If it doesn't tell me one, my default is 5%. So with that significance, I wanted to just do all the work and spit out the pile of answer in a separate page. Well, this is helpful. Okay. Please note, the upper part of this table says summary. The bottom part of it says ANOVA. So the answer to my question is found in the bottom. But some useful information comes out of the top. It asks, what is the source of the variation from the rows, from the columns? I need you to answer the question. Does which row I'm in matter? That would be which Friday it is, correct? The rows were the dates. So, does which row I am in affect absenteeism? My null hypothesis was that it didn't matter. So I need to know, do I accept or reject that null hypothesis? For the rows,
Here then our value.
And-
Maybe one can assume that it is the folded F test.
well, since there's only one value given, I would have to make that assumption.
Exactly, so this value is bigger, it's a right tail test, and the critical value is smaller, so we are in rejection.
Which means we reject the null hypothesis. Which row we are in does matter. The Friday matters. Now, if I go up and I look now at the row information up here in my summary, yeah, it looks like one particular Friday, the average absenteeism was a bit higher than others. I see here the middle row has an average of 25, the other two rows 21 and 22 respectively. And the F value being bigger than the F critical tells me it is not just an arbitrary difference, it is a statistically significant difference. What's the other way I could have figured out that same result? My p-value. When I go to the rows, the p-value is very small. It's smaller than 0.05, therefore that matters. Now, what about the plant? Does which plant I'm at matter?
Yeah, the calculated values again are bigger.
And in the same sentence, my p-value is really, really small. So it's much smaller than 0.05. And to me, that says that one matters more. It's a much stronger significance effect because the p-value is much, much smaller than it is for the rows. So here, yeah, which plant I'm at makes a lot more difference than which Friday it is. As a matter of fact, again, I go back up here and I look at the averages across my plants and I see, oh, yeah, I've got 18 and 20, and then I've got 25 and 29. Two plants have substantially more absenteeism on Friday than the other two. Today's a Wednesday, so I don't care. But in general, now I can sort of track these things. The smaller my p-value means the more of an effect I have. The larger difference between F calculated and F critical means the larger effect I have here. That factor matters more. Questions? It is possible to do as many factors as you want. The calculations get larger, longer, and uglier, but the process is the same. And for each different layer of factors, I'm going to get another F test. So if I had 3 factors, there'd be 3 F values, 4 factors, and so on. These get much harder to compute, and they're not actually in Excel.
Just look at the rows and columns not together, that we can see.
Well, at this point, I'm treating them separate. If I want to look at how A and B combine to give me stuff, that's a little harder. And then it would be really kind of odd because I only have one piece of data for each one, right? When I go back to the data itself, I only have one piece of information on March 11th out of plant 2, right? And I think, I mean, it would be difficult to get multiple information from one location. I think this actually prevents me from looking at interaction behavior that way. But that's the setup for this experiment, right? So what if I was thinking about school districts, right? I could think about high school absenteeism, middle school absenteeism, elementary school absenteeism. There'd be multiple schools in each setup. Then I might be able to look at whether or not it's within the factor. More questions? It is possible and often the case that while I have multiple factors involved, I really only care about one of them. So a confounding influence. Perhaps it's not fair of me to look at these 3 Fridays all equally, because it might be that one of those Fridays happened to be the day of the big game. Or it might be that one of those Fridays, there was a really good band in town that night and everybody was going to that concert. Hey, Taylor Swift came to town. Nobody's going to be anywhere at school. We're not staying to the plant. Or maybe it was a Thursday night concert. Nobody shows up because they're all home, nursing themselves back to health. Well, that idea of controlling for a confounding factor is sometimes called a control group. We might say we're measuring fertilizer performance on plants. And if we're measuring the fertilizer performance on plants, then the type of ground we're using might also have an influence, right? The type of soil itself. Are we using fresh potting soil? Are we planting these outside, inside? So there may be some other factors that we want to control for. Well, then I'll take my setup and I'll randomly assign any subject to a given block in a treatment. So I've got 5 different types of dirt. Some of them are going to get with fertilizer, some of them are going to get without. It'll be randomly decided. But my goal is eventually I'll be able to put everything to everybody to complete that grid that we have. The difference is really only in the interpretation. Almost always, we use the blocks to be the rows. And the treatments are the columns. So if I'm looking at all these different kinds of fertilizers, I'll randomly assign soils to fertilizers, but then I'll list the soil types in the rows, and I'll list the fertilizers in the columns. Because I only care about did the fertilizer have an effect. I don't care about the dirt. I care about what I added to it. Maybe I really didn't care about which Friday it was. I just cared whether the plant mattered. And then the interpretation really just ignores the other F value because we're controlling for something instead of trying to check and see whether it mattered. I didn't pull that example about dirt and fertilizer arbitrarily. Page 429 uses exactly this idea. We have a North Dakota agriculture business is wanting to know whether or not the fertilizer it uses has an effect on growing. But, people grow in all sorts of different soil types. So we'll just, here, 3 different types of dirt. We'll plant wheat in everything, and then we'll use the 4 different types of fertilizer. I really only care about the column effect. I don't really care about the row effect. So I will measure them both in my ANOVA, but I'll really only care about the result for the columns in this setting. Just like our Friday and our plant. Maybe it's the Friday that matters, maybe it's the plant that matters. Questions? This is referred to as a randomized block model. If you read a paper, a business paper, and they're talking about setting up risk portfolios and looking at different types of, I don't know, immunization across a economic model, and they're looking at, okay, well, if we put out this value of immunization, do we actually profit or loss? Well, then what the portfolio risk value is matters. The type of risk in the portfolio, I can say, oh, I'll look at how it affects low ones and medium ones and high ones. And then I'll be able to say the different types of risk evaluations and my return on investment. And I can say, oh, did my risk evaluation matter based on what risk level I had? Problem number 23. Driving time from the airport to a downtown hotel is recorded for 5 Uber drivers. Is there a difference depending on which hotel I'm going to or which driver I get? Are some drivers really, really cautious? Or are some of them pedal to the metal speed demons going down Green Tree Hill coming back from the airport? Again, what's my null hypothesis? Felix?
That there's no significant difference.
In the drive time. And Tony for the other one? And then for the hotels. There's another null hypothesis, right? What's the null hypothesis for the hotels?
Like drive time to get to each hotel is not significant, the opposite.
At least one is. So the null hypothesis is there's no difference between the drivers. Whichever driver I pick, I'm going to get there in the same average time. And there's no difference in the hotel, whichever hotel I'm going to. I'm going to get there in the same average time. But I only have one record for each driver to each hotel. Let's see what happens. Here is my drive time data. If you've got your computer in front of you, go grab this file off the Doan site We've got this. You should be able to do this right along with. All of the, we're in chapter 11. So all of the files are here in the chapter 11 zip. This is one of the exercises. So once you open that, it'll be under exercises. This is number 23, right? Yes. Absences was 21. Drive time is number 23. It should also be on our Canvas page directly, available for you to download as well in the files section. There, chapter 11, drive time. I want to run what test here? I go to my data section, tell it to do the analysis, but I got to know what I want it to do. What do I want it to do for me? But there are 3 of those. Without replication, 2-factor. Poof. All right, let's make sure we have the right stuff highlighted. Oh, I don't. I need to go out another row and down another column, Now I have the right stuff highlighted. I have the labels in there because it says driver A, B, C, D, E. Put it in a new spot. Here's my giant pile of information. You'll notice that it squishes that first column. I can't quite read the top there that says something here. So I'm going to blow that column up a little so I can see it better. Okay. Again, notice rows, then columns. Up in my summary information, it just says hotel and driver. It doesn't tell me which is which. But down in the ANOVA, it says rows first and then columns. So the summary data is in that order, rows first, then columns. So what matters, what doesn't? Good. If you have a question, or are you going to answer stuff?
Yeah. What matters? I thought we just again look at rows and columns. And we look at the calculated value of 1.11 and the critical value, and our calculated value is smaller than the critical value. So we don't need to reject it because
It's in the white, the non-reject area. The rejection area is up there in the top when it's bigger than the value. Or look at the other value in there, the p-value.
yeah, also.
And I want my p-value to be small for me to reject the null hypothesis. So if my p-value says, or my critical and calculated value says, don't reject for the rows, what does that mean in this setting?
There's no huge difference between the hotels based on their driving time.
Because the rows represent the hotels. Your choice of hotel does not affect your drive time. They're all effectively the same time away from the airport. Now, I have no idea where we are. Kansas City, Pittsburgh, which airport we're at. We're at Latrobe Airport. Which hotels are we going to? But they're all the same time away. Any variation based on what time I'm looking at has not been affected by which hotel I tell them to go to. All right, with that in mind, what about the columns? Anthony?
Closer, but same, the. Or is that value smaller?
Oh, man. That is really freaking borderline, isn't it? Look at that. 3.2590 is the calculated one. 3.2591 is the critical one. Oh man, is this close? Is it bigger than the critical value? No. But oh my gosh, I had to go out 4 decimal places. This is really close. But again, I'm going to say the same thing. Look at the p-value. 0.050000006. I'm just barely above 0.05. Technically, since it's above 0.05, what do? Fail to reject. So which driver you get doesn't really matter. Hang on a second. Which driver you get doesn't really matter? Look at the average drive times by driver. It's pretty clear one of these people has a distinctly larger average than the other, right? But what we're saying is that the standard deviation, the spreads here, are kind of uniform around the gross average. The average within my columns, which isn't visible in my calculation down there for the ANOVA. I haven't done a grand average by columns. I could sit down and average those 5 numbers. The average is 26 and a quarter. I noticed there are 2 26s, and then there's a 25 and a 22 and a 30. So it seems to be fairly symmetrically spread. It's unlikely that we're really off to one side with one huge outlier. There's just as much below the average, the grand average, as there is above the grand average. So it's really, 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 really close. If I were the person conducting this survey, if somebody had paid me, my consulting firm, and said, I want you to tell me whether or not my driver matters, I'd be like, dude, I need more information. Because right now I am right on the border of being able to tell you yes or no. So let me get another, 5 pieces of hotel runs for each one. Another 4 hotel runs for each one. Let me get more repetition. And maybe I can learn more about what's going on. But when I gather repetition, maybe there's a traffic jam one time and there wasn't another. There can be variation now within a single treatment. Right now, there's no chance of any influence on driver B going to hotel 2, because I only have one number. If I have multiple numbers for driver B going to hotel 2, then it's possible that there'll be variation within that as well. That is another concept I need to take into account when I start to work on what should happen within my ANOVA behavior. Questions about 2-factor? If I am missing numbers, I have a problem. If I didn't ever get driver A going to hotel 4, I'm going to be in deep trouble here. Missing data is absolutely a problem in single without repetition ANOVA. It is also fairly common to end up with missing data. So Y'all took DT 100 or have taken or will take DT 100. You talk about data cleaning and scrubbing and trying to figure out how do you deal with this missing data. These are the reasons I need to be careful of that. If I'm missing data, I might end up with some really, really skewed results here. More on that in the next chapter as well, because we'll be able to account somewhat for this if we have repetition. Questions? You all have an exam coming up. Any questions about that? I'm going to be really nice to you. Get out of here. I'll see you Friday for the exam, and I will have this homework key posted in about 3 more minutes. Yes, you absolutely should take a picture if you want to have it while you study, but the key will definitely be up.